A definite integral calculates exact accumulated value, like total area, mass, or energy, trapped between two rigid physical boundaries. When solving calculus problems using traditional analytical methods, you calculate row by row through an exhaustive set of operations. Applied computational logic operates differently. In software, that entire dense calculation can often be replaced by a single command: return 0. Moving from manual calculation to optimized code depends on how the algorithm interprets these integration limits. Computational hardware will blindly iterate through millions of unnecessary floating-point operations, wasting processing power and memory if engineers fail to optimize these limit parameters. We eliminate this waste by applying two rigorous mathematical concepts: variable substitution tracks and structural parity. Leveraging these specific calculus rules provides an optimization bypass, allowing systems in aerospace, electronics, and software engineering to arrive at the solution without rendering the full calculation. To simplify complex functions, we frequently substitute variables, swapping the original variable x for a new variable u. This animation shows a one-dimensional number line along the x-axis. When the underlying variable changes, the boundaries physically shift to match the new domain. The original limits, a and b, lock into translated limits, g of a and g of b, filling the active calculation zone. A common inefficiency is attempting to back-substitute the new variable u into the original variable x to evaluate the integral. With definite boundaries, once you move into the u domain, you never convert it back to x. Executing the calculation entirely within these newly translated limits strips out redundant algebraic steps. The domain translation mathematically isolates the system. The old variables are rendered computationally obsolete. Calculations change when the boundaries are perfectly symmetric, spanning from negative a to positive a. Under symmetric limits, we evaluate the function's structural parity. The first type is an even function, mathematically defined as f of negative x equals f of x. Here is the parabola y equals x squared. The area from negative a to 0 geometrically mirrors and folds across the y-axis. Due to this symmetry, we take an operational shortcut, isolate the calculation from 0 to a, and simply multiply by 2. The second type of structural parity is an odd function, defined where f of negative x equals negative f of x. Plotting y equals x cubed reveals an odd function acting as a negative inverse. The red negative area in quadrant 3 opposes the blue positive area. As we evaluate the span, the negative area sweeps up and annihilates the positive area, yielding exactly 0. By determining structural parity up front, engineers entirely bypass the mechanics of full integration. We anchor this symmetry rule to physical aerospace mechanics. Calculating structural integrity requires determining the center of gravity and aerodynamic loading distribution across the airframe. This head-on vector model of a delta wing demonstrates steady, level flight. The wingspan acts as our x-axis, from negative a to positive a, and the uniform upward vectors represent a physical even function. To calculate total lift, fluid simulation software integrates the aerodynamic forces, starting from the fuselage centerline out to just one wingtip. By treating the steady aircraft as a symmetric even function and doubling this half-span calculation, the software reduces simulation rendering time. That steady state ends the moment the aircraft initiates a roll maneuver. As the pilot applies differential aileron deflection, lift vectors on the left wing point downward, while right wing vectors point upward, forcing the load into an odd function. The upward force on one side perfectly cancels the downward force on the opposite side. The net change in vertical lift across the wingspan evaluates to 0. The odd function dictates that the aerodynamic energy is converted entirely into a rotational moment, creating torque. Mathematical parity strictly governs electrical hardware and signal processing as well. When evaluating alternating current over a full symmetric wave cycle from negative t/2 to positive t/2, we face a boundary integration. This diagram plots a pure, undisturbed AC sine wave over that symmetric axis. The positive crest and negative trough mirror each other inversely, forming a natural odd function. Over one cycle, the positive voltage perfectly cancels the negative voltage, leaving a net integral of 0. However, an engineer designing a power supply must calculate power dissipation to determine the thermal load. Net voltage is not enough. This requires evaluating the power equation, P equals V squared divided by R. Squaring the alternating voltage strips away its negative properties. The trough abruptly flips above the axis, forming continuous positive humps. The exponent strictly forces the AC signal into an even function. With the parity shifted, the cancellation disappears. The energy strictly accumulates and physically dissipates as heat, dictating exactly how the hardware must be designed. Executing these aerospace and electronic simulations requires optimized software architecture. A CPU running advanced fluid dynamics or a real-time physics engine faces an immense computational burden. The brute force approach to solving symmetric systems is forcing the processor to iterate 10 million individual floating point calculations across boundaries from -n to +n. We avoid this entirely through algorithmic calling, applying calculus proofs to stop calculations before they run. By writing a conditional check to identify an odd function up front, the system recognizes the structural parity and immediately returns a 0 without attempting to calculate the area. This single conditional check collapses a linear O of n computational workload down to a fraction of the processing space. It reduces the operation to constant time complexity, a necessary method for preventing hardware memory bottlenecks during complex simulations. By exploiting structural parity, engineers bypass billions of redundant operations in flight simulations and power circuit designs.